In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about a static field modeling of a Halbach rotor. A static field modeling is the process of creating a computer model of a system's properties that don't change over time, such as electric or magnetic fields. It is used in various fields like software design, reservoir engineering, and electromagnetics to simulate static structures and calculate properties based on fixed conditions. A static model is essential for providing a baseline reference that can be used for further analysis or as an input for more complex dynamic simulations. And what are the applications and types? The first one is software engineering. A static model describes the fundamental structure of a system, defining its classes, attributes, and relationships independent of time varying functions. The next application is reservoir engineering. This type of modeling creates a static model of a subsurface reservoir which represents the distribution of rock and fluid properties. It is used to estimate the amount of hydrocarbons in place and serve as a reference for planning future wells. The next application is electromagnetics. This involves modeling static electric and magnetic fields which are created by stationary charge and currents. These models can be used to simulate the fields from permanent magnets or calculate magnetic flux density. The next application is crowd dynamics. This involves using static fluid field models to simulate the escape paths of people in emergency where the field represents fixed factors like exits and obstacles. The next application is general systems. Static models can also represent any system with properties that are time independent, such as calculating a system's mass or volume. And what are the key characteristics? The first one is time independent. The model represents a system at a single point in time or one where time is not a factor. The next is defines structure. It defines the fixed components of a system such as geometric properties of an object or the classes in a software program. The next characteristic is serves as a baseline. A static model can be used as a foundation for more complex dynamic models which incorporate time-varying changes. The next is calculates static properties. It is used to determine values that are constant, such as physical properties, for example, mass, volume, or field strength at specific points. The next one is input for simulation. Static models often provide and the necessary input for dynamic simulations to run effectively. And what about the definition for Halbach array? A Halbach array is a special arrangement of permanent magnets that augments the magnetic field on one side of the array while cancelling the field to near zero on the other side. This is achieved by having a specially rotating pattern for magnetization. The rotating pattern of permanent magnets on the front face, on the left, right, and down can be continued indefinitely and have the same effect. The effect of this arrangement is roughly similar to many horseshoe magnets placed adjacent to each other with similar poles touching. This magnetic orientation process replicates that applied by a magnetic recording type head to the magnetic tape coating during the recording process. The principle was further described by James Vinnie of Magnepin in 1970 for the ideal case of continuously rotating magnetization and induced by a one-sided stripe-shaped coil. The effect was also discovered by John Mallinson in 1973, and these one-sided flux structures were initially described by him as a curiosity. Although at the time he recognized from this discovery the potential for significant improvements in magnetic type technology. Physics Klaus Halbach, while at the Lawrence Berkeley National Laboratory during the 1980s, independently invented the Halbach array to focus particle accelerator beam. The next is linear array magnetization. The magnetic flux distribution of a linear Halbach array may seem somewhat counterintuitive to those familiar with simple magnets or solenoids. The reason for this flux distribution can be visualized using Mallinson's original diagram. Note that it uses the negative Y component unlike the diagram in Mallinson's article. The diagram shows the field from a strip of ferromagnetic material with alternating magnetization in the y direction, top and left, and in the x direction, top and right. Note that the field above the plane is in the same direction for both structures, but the field below the plane is in opposite directions. The effect of superimposing both of these structures is shown here. The crucial point is that the flux will cancel below the plane and reinforce itself above the plane. In fact, any magnetization pattern where the components of magnetization are out of phase with each other will result in one-sided flux. The mathematical transform that shifts the phase of all components of some function by is called a Hilbert transform. The components of the magnetization vector can therefore be any Hilbert transform pair, the simplest of which is simply as shown here. And what are the applications? The advantages of one-sided flux distributions are twofold. The first one is the field is twice as large on the side on which the flux is confined. In the idealized case, the next is there is no stray field produced. In the ideal case, on the opposite side, this helps with field confinement, usually a problem in the design of magnetic structures. Thus, they have a number of applications ranging from flat refrigerator magnets through industrial applications such as the brushless DC motor, voice coils, magnetic drug targeting, to high-tech applications such as Wigler magnet used in particle accelerators and free electron lasers. The Inductrack magnetic and Inductrack rocket launch system utilize the Halbach array to lift the train by rippling loops of wire in the track. And flexible, not hard ceramic ferrite refrigerator magnets are created with a Halbach magnetization pattern for a stronger holding force when attached to a flat ferromagnetic surface, for example, a fridge door, than the holding force from a uniform magnetization. They are made from powered ferrite mixed in a flexible binder, for example, plastic or rubber, that is exposed to Halbach magnetization field pattern as it is extruded, permanently giving the ferrite particles in the magnetic compound this one-sided flux distribution which can be viewed with magnetic viewing field. Scaling up this design and adding a top sheet gives a Wigler magnet used in synchrotrons and free electron laser. Wigler magnets wiggle or oscillate an electron beam perpendicular to the magnetic field as the electrons are undergoing acceleration. They radiate electromagnetic energy in the flight direction, and as they interact with the light already emitted, photons along its line are emitted in phase, resulting in laser-like monochromatic and coherent beam. The design shown above is usually known as Halbach-Wigler. The magnetization vectors in the magnetized sheet rotate in the opposite sense to each other. Above and the top sheet's magnetization vector rotates clockwise, and the bottom sheet's magnetization vector rotates counterclockwise. This design is chosen to that the X components of the magnetic field from the sheets cancel and the Y components reinforce so that the field is given by where K is the wave number of the magnetic sheet given by the spacing between magnetic blocks with the same magnetization vector. Variable linear arrays, a series of magnetic rods magnetized perpendicular to their axis, can be arranged into a Halbach array. If each rod is then rotated alternately through 90 degrees, the resultant field moves from one side of plane of the rods to the other. As shown schematically in the simulation, this arrangement allows the field to effectively be turned on and off above or below the plane of the rods, depending on the rotation of the rods, such as device makes an efficient mechanical magnetic latch requiring no power. A detailed study of this arrangement has shown that each rod becomes subject to a strong torque from its neighboring rods when rotated. However, a simple and efficient solution providing both stabilization and the ability to rotate each rod alternately is simply to provide an equal gearing arrangement on each rod, as shown here. And what about the sealant? A Halbach sealant is a magnetized sealant composed of ferromagnetic material producing, in the idealized case, an intense magnetic field confined entirely within the sealant with zero field outside. The sealants can also be magnetized such that the magnetic field is entirely outside the sealant with zero field inside. Several magnetization distributions are shown here. The direction of a magnetization within the ferromagnetic material in plane perpendicular to the axis of the sealant is given by here. When MR is the ferromagnetic remanence based on ampere per meter, a positive value of K subtract to 1 gives an internal magnetic field and a negative one gives an external magnetic field. Ideally, these structures would be created from an infinite length sealant of magnetic material with the direction of magnetization continuously varying. The magnetic flux produced by this ideal design would be perfectly uniform and be entirely confined to either the bore of the cylinder or the outside of the cylinder. Of course, the idealized case of infinite length is not realizable, and in practice, the finite length of the cylinders produced end effects, which introduce non-uniformities in the field. The difficulty of manufacturing a cylinder with a continuously varying magnetization also usually leads to the design being broken into segments. And what about the applications? These cylindrical structures are used in devices such as brushless AC motors, magnetic coupling, and high field cylinders. Both brushless motor and coupling devices use multiple field arrangements. The first one is brushless motor or alternators typically use cylindrical design in which all the flux is confined to the center of the bore, such as K is equal to 4 above a 6-pole rotors. With the AC coils also contained within the bore, such self-shielding motor or alternator designs are more efficient and produce higher torque or output than conventional motor or alternator designs. The next one is magnetic coupling devices transmit torque through magnetically transparent barriers. That is, the barrier is a non-magnetic or is magnetic but not affected by an applied magnetic field. For instance, between sealed containers or pressurized vessels, the optimal torque coupling consists of a pair of coaxially nested cylinders with opposite positive core and negative core flux magnetization patterns. As this configuration is the only system for indefinitely long cylinders that produce a torque. In the lower Lowest energy state, the outer flux of the inner cylinder exactly matches the internal flux of the outer cylinder. Rotating one cylinder relative to the other from this state results in the restoring torque. Cylindrical Halbach arrays are used in portable MRI scanner. They offer the potential for a relatively lightweight, low to mid-field system with no cryogenic electromagnetics, a small fringe field, and no electrical power requirements or heat dissipation needs. The reduced X-ray fields also enhance safety and minimize interference with surrounding electronic devices. And perfect pole positioning. Halbach rotors are notoriously difficult to manufacture due to the large magnetic forces between the radial and tangential magnets. Our patent manufacturing process allow us to assemble Halbach rotors with perfect magnet positioning in a rapid and repeatedly manner. Our expertise in manufacturing Halbach array rotors allow us to deliver products with tight tolerances and cost effectiveness with precision engineering at the core of our process. We ensure that every rotor meets stringent quality standards, guaranteeing reliability and performance consistency across our product range. And what about maximize performance? By incorporating Halbach array rotors into our slotless motor, Alba achieves unparalleled levels of torque density and efficiency, even rivaling the performance of the best slotted motors. Maximize performance by incorporating Halbach array rotors into our slotless motor. Alba achieves unparalleled levels of torque density and efficiency, even rivaling the performance of the best slotted motors. This model, this model presents the static field modeling of an outward flux focusing magnetic rotor using permanent magnets. This magnetic rotor is also often called a Halbach rotor. The use of permanent magnets in rotatory devices such as motors, generators, and magnetic gears is increasing. The accurate modeling of a permanent magnet's field is important. This model illustrates how to calculate the magnetic field of a three-dimensional rotor by modeling only a single pole of a rotor using the symmetry features. This example presents the static field modeling of an outward flux focusing magnetic rotor using permanent magnets. A magnetic rotor, also known as Halbach rotor, the use of permanent magnets in rotatory devices such as motors, generators, and magnetic gears is increasing due to their no contact, frictionless operation. This model illustrates how to calculate the magnetic field of a four-pole paired rotor in the three-dimensional by modeling only a single pole of the rotor using symmetry. Model definition set up the problem in a three-dimensional modeling space due to symmetry. It is sufficient to model a single pole of the rotor, and here you can see that this picture shows a three-dimensional view of the complete rotor with the magnetization direction of the magnets indicated. The black arrow shows the radial and axial magnetization direction of the permanent magnets in the rotor. The permanent magnets are arranged in such a way that the magnetic flux density is minimized inside the rotor and maximized outside the rotor. The model consists of 16 permanent magnet pieces arranged from a four-pole pair rotor. The inner and outer rotor radial are 30 millimeter and 50 millimeter respectively. The axial length of the rotor is 30 millimeter. A steady-state study analysis is performed to calculate the magnetic fields of Halbach rotor. The magnetic flux density is shown here, illustrate the variations of the radial and azimuthal magnet flux density as functions of rotor angle. The magnetic flux density norms is evaluated outside the Halbach rotor at a radial distance of 55 millimeter from the center. Finally, the last results show the polar plots of the magnetic flux density norm at radial distances from the rotor center of 55 millimeter and 25 millimeter respectively. And here you can see that I have used the magnetic fields as a physical module with the free space, magnetic insulation, initial value, and magnet. And the geometry is part of the here that will be in the mesh, as a tetrahedral mesh, and you can see the B field and the plot for magnetic flux density, and also norm B versus phi at 25 millimeter, and here is the 55 millimeter. Thank you so much for watching my video until the end, and also you can download this simulation from github.com/math.